Hello, this video is going to be about zero placement, and to start out with, what I'm going to do is define a velocity control system. This is like a open loop gain, corner frequency, and this would be a velocity mode, and then if I divide by S, I integrate velocity into position. So this is a open loop position system. This is my PID controller. And to define my zeros, what I'm going to do is use my standard definition for closed loop transfer function, which is with the gain or the controller up here. But this is going to have a z. That means we're working on the forward path, or these terms are going to be multiplied by the difference in error only, and you'll see that below. So these variables work on the full state. This is the feedback path. This is the forward path. And the integrator doesn't change, but the proportional gain does, and the derivative does. And basically, other people call this 2 degree of freedom. And what they'll do is they'll have the Kp here with the coefficient, like a weight P, and then this will be the derivative gain with a weight D. But I just combined the two terms together so that it's not quite as messy. So going on, I'm going to simplify this. And here you can see the simplified with quotes. And you can see that these special gains only occur in the forward path. This is the characteristic equation, and you can see that the Ki, Kp, and Kd do not change, whereas the gains in the forward path do. So now I'm going to define a closed loop or desired characteristic equation, and I want to have 3 poles placed at minus lambda. So if I expand this out, this is what I get for my powers of S. And I'm going to use my shorthand way of calculating the symbolic PID gains. And basically all it's doing is it's taking this lambda cubed and matching it to this. So if I take Ki is equal to lambda cubed divided by K times alpha, and that would be my Ki term. This would be the Kp term here and the Kd term here. And then this is S to the third power in both cases, and there's nothing to be gained from that. So I end up with my 3 gains, Ki, Kp, and Kd for my PID gains. But those are the gains that are used in the feedback path. Now, in the forward path, I want to place zeros, and I'll show you why I want to place zeros in a little bit here. So this is my equation for the numerator of the closed loop transfer function above. And let's see, let's just move up above here. That's this. And what I want to do is place the zeros. So what I need to do is here is my the equation from above. I don't need the K and the alpha because that doesn't affect the zeros. And I need to divide by the derivative term in the forward path, so that the S to the power, or the second power of S, is has a coefficient of 1. So this will be Kpz over Kdz times S and Ki over Kdz. And then I'm going to make a substitution for Ki, and this is from the symbolic gain from up above. And the Ki never changes, whether it's in the forward path or the feedback path. So now I'm going to do the same thing that I did before. I have 2 equations. This is what I desire. So this is where I want to have the zeros. And the zeros are going to be some fraction of lambda, which is where the poles are. So this will allow me to place the zeros on the negative real axis, either closer to the origin if this is less than 1, or farther away from the origin if C is greater than 1. So after subtracting these out, I get this difference. And basically what I'm doing here is I'm equating the this KD to, well, I have to kind of combine this, and this is what I end up getting is the forward path proportional gain is this term, and the forward path derivative term or gain is this term. So let's define some parameters and see how this works. So I have the open loop gain, and I chose 10 millimeters per second per percent, which would allow the system to go as fast as 1 meter per second. 100% times 10 would be 1,000 millimeters per second. I have a corner frequency of 10 hertz, which isn't real high, but it's a nice round number. And this would be the time constant. Let's move on down a little bit here. I want to have the closed loop poles placed at the same point as the corner frequency. Now we'll change this a bit. I can make it faster. In fact, that's one of the benefits you get from having a motor controller and an amplifier, is that you can increase the bandwidth of the system. Then C happens to be what fraction of lambda where I've put the closed loop zeros. So the closed loop zeros are going to be basically 8/10 or 4/5 of whatever lambda happens to be. And you'll see that's a pretty good location. Now I'm going to have my standard symbolic equations. This doesn't seem to change at all, depending. This is still Ki, Kp, and I have many worksheets where these formulas are derived. But the feedback path or the forward path gains, Kpz, are from above. Let's go back up. They're up above this, and this get set to Kpz and Kdz. So these are the gains that work on differences in the target. So now let's do a simulation. So I have my simulation, and because I've got a integrating system, I need to have zeros here. This is my corner frequency, and this is the numerator, the open loop gain. I got interval, identity matrix, but the identity matrix isn't necessary here because I'm not using exponents to calculate what the digital or discrete A and B matrix happen to be. So these are the A and the B matrices, and I kind of added the K into the B matrix. Normally you see B times K in the formulas, but I just kind of combine them into one. And this isn't necessary. This is if you're going to do the simulation in discrete mode, but you can see that I'm using state space. And also I derive these equations using the Laplace method for converting doing a matrix exponential. And this is the most accurate way of calculating the matrix exponential. So let's go on down. This is the simulation, and this is my state space update. So I have R, which is my target position, X, it's actually a target position and actual and target velocity, and this is my actual position velocity. This is my last reference, and this is my control output. So this is updating the state. So this is the new state. X is the last state. And what's interesting here is I'm using the incremental mode to update my control output. So I have the integrator gain multiplied by the time constant. This makes it so that it's independent of the scan time, because the scan time is always going to be taken into account here. And this is the target position minus the actual position. So this is the integrator part. And then this part, I have the forward part, the forward path gains, KPZ and KDZ, and they're multiplied by, this is a two-dimensional matrix. This is the last target position and target velocity subtracted from the current target position and target velocity, and I multiply this out. And then this is the what you would get in a normal PID, where you have KP and KD multiplied by the this is a vector with the actual velocity or position and velocity. So then I return the new state and the control output. Plus I'm limiting it to plus or minus 100%. And what I like about the incremental mode, or what a lot of people call the velocity mode, is you don't have to worry about integrator windup. And just to test that out, I did a simulation where I'm doing some changes in the position. And you can see that my changes, I'm doing a change of 100 millimeters, and you can see that it's kind of racing right up to 100 millimeters, but it doesn't overshoot. And you can see why in just a moment. Then you can see that I'm moving it down and then back again. And what I like to do is test to make sure that the system handles saturation well. And you can see in this example it does. So now I'm going to show you a sine wave. And I've got a 50 millimeter amplitude sine wave going at 2 hertz. And you can see there's a little bit of phase lag, but the amplitudes are about right. And I'll show you why right here. This is my Bode plot. Let's go back up a little bit. And we have the closed loop transfer function. And these are the forward path gains. And these are the feedback path gains. And you can see that the response is almost flat, but at 2 hertz, you can see there's a little bit of phase lag, but the amplitude doesn't change much. The amplitude is close to unity. So what we should see is some phase lag, but the amplitude shouldn't change. So that's about what we see right here. A little bit of phase lag, and the actual position and the target position are about the same in the amplitude. So let's graph the poles and zeros. And here you can see the zeros are 0.8 or 4/5 of the way to the poles. So there's 2 zeros here and 3 poles here. So altogether, the system should act like a single pole system at 10 hertz, because that's where we set the lambda to. And if you take a look, um, well, I set the zeros are not at lambda, so I get a little bit better bandwidth than 10 hertz. So let's go up and play with this some. Let's place all the zeros. Let's place this C, make it 1. So what will happen is the 2 zeros are going to be at the place of 2 of the poles, and they'll cancel out, so there's only 1 pole, effectively. And you can see that the response is pretty good. There's a little bit of phase lag. It's a little bit more phase lag. And you can see that this is just a little bit more at 2 hertz. And if we go down here, you can see the bandwidth is 10, which is what you'd expect if you had only 1 pole at 10 hertz. So you can see the bandwidth is 10. So you can see that when I had the zeros closer to the origin, they tend to increase the gain and the phase lead a little bit, so you get a better bandwidth. So the point is that zeros will increase the bandwidth and enhance performance, but there is a downside. You can only do this so much. So I'm going to go back and show you what happens when I change the bandwidth to something like 1/2. So now the zeros You can see that there's an awful lot of overshoot, and you can see that the overshoot is caused, you can see this by the Bode plot. So at 2 hertz, there's a little bit of overshoot, and there should be a little bit of phase lead. And what you can see is that these 2 zeros are 1/2 of whatever the 3 poles are. So as you scan from the origin going to the left, these will start to affect the response first. So they'll start adding gain and phase lead. And then eventually, as you approach the poles, they start adding phase lag and a decrease in gain. So optimal seems to be about 0.8. So let's just go back to 0.8 or 4/5. Oops, went too far. So let's make this 4/5. Oh, um, yeah, 4/5. So now by making the zeros 4/5, you can see that I track pretty closely here. And also my bandwidth has increased from 10 hertz to, which is the open loop gain, to 17 hertz. So there's an advantage to using zeros and placing them at the right position, just a little bit to the right of the closed loop poles, but not too far from the right because it will cause overshoot. So now let's go on to a new topic, which is using the poles and or the zeros to make a notch filter. So I have to first undefine my variables so that I can use them again symbolically. And this is my notch filter. This is the quality factor. And this is where the notch filter is going to be. So I expand that out. This is what I get. And again, this is the numerator from the simplified closed loop transfer function from above. And basically, I do the same thing that I did before. This is the same equation. And the only thing that's different is that instead of setting this equal to S plus C times lambda to the second power, I set it to the notch filter formula. And then I solve for the gains. And these are the forward path gains for the proportional gain and the forward path derivative gain for the notch filter. So now let's go down, and I got a Q factor of 5,000. Normally, when the higher the Q factor, the narrower the filter is going to be, and I want this filter to be at 10 hertz. So I got a notch filter at 10 hertz, and so I've initialized, or I set the forward path proportional gain derivative gains to their formulas and do the calculations and do the simulations, and you can see that it doesn't change the step response at all, and it doesn't really look like it's changing. Well, you can see that it's changing the response for the sine wave by quite a bit, because at 0.8 this was they're almost identical. They're a little bit of phase lag. So you can see that the notch filter is starting to have an effect on the response. And then this is the Bode plot. And here you can see the notch filter, the effect of the notch filter. And you can see that it's really pretty sharp. If I reduce the value for Q, this will become a little bit whiter. Now let's do something interesting here. Let's make the notch filter at 2 hertz, which is where the frequency of the sine wave happens to be. So let's make it 2 hertz, and see, it doesn't affect the step jump at all, but the sine wave, it pretty much knocks out the response for the actual target position, or the actual position and actual velocity. And we have used this a couple times in the past, uh, normally just to make it so that the motion controller doesn't respond to machine resonances that happen to be around 8 to 10 hertz. And you could use it to reduce 50 cycle or 60 cycle hum too, if you happen to have a feedback that's susceptible to that. So now let's go back and put that back equal to, let's make this 20. You can see that it's moved up to about 20. So the point is that you can, by adjusting the zeros and placing the zeros, you can uh, add features that you want, like a notch filter, without actually having to add yet another notch filter. And also, eventually what happens is that the systems will become much more complicated. Like this is a hydraulic system, and you can see that this has got the equivalent of a notch filter, but this is accidental. I wasn't planning on getting this, just that the natural values for the Ki, Kp, Kd, and the second derivative gain just happen to create this notch filter, and it's not necessarily desirable. So I would want to use the zero placement to try to level this out. So the point is that eventually what you end up looking at is that the closed loop transfer function is just a polynomial with a numerator and a denominator, and it could have any number of terms. And it requires a little bit more mathematics if you're going to have something to the third power, like this is, well, this is actually a fourth order system here. And so the mathematics gets to be a little bit more difficult. I didn't want to show this or do the math, but I did want to show the effect of what the zeros can have, and they can be an unknown gotcha if you're using the wrong values of P, I, and D, even if you are placing the closed loop poles where you want them. So that's the point that I want to make. Hope you enjoy the video. Goodbye.